Hello everybody, this is Dr. Christopher White and welcome back for part 2 of the Precambrian and its life history, focusing on the Hadean and the Archean. So now we're going to start thinking more about oceans. So analysis of rocks from the Ishiwa Greenstone Belt of Greenland and the Nuvagatuq Greenstone Belts of Canada have identified pillowed basalts dating from 3.8 billion years in the case of the Ishiwa Greenstone Belt, and between 4.28 and 3.8 billion years in the case of the Nuvagatuq Greenstone Belt. So the pillowed basalt texture is actually quite helpful to us. The vast majority of pillowed basalts are formed at divergent plate boundaries, so the presence of this texture would suggest that there may have been divergent plate tectonics working during this time period. Now, even if these pillowed basalts aren't due to divergent plate tectonics, let's say they're due to a hotspot, for instance, like Hawaii, the presence of this texture tells us that the magma was being extruded onto a stable piece of crust, because that piece of crust has survived all this time. So that at least tells us that we would have had stable pieces of crust, on the surface of the Earth at that time. But the key thing about the pillowed basalt texture is that in order to form a pillowed basalt texture, you have to have magma being extruded onto a seafloor. And obviously to have a seafloor, you have to have a sea. So the presence of this texture is a very strong indicator that there may have been bodies of liquid water on the surface of the Earth all the way back around 4.28 billion years ago. Now, it's difficult to exactly identify the point where ocean formation would have occurred. You have to remember we're dealing with rocks which are old, they've often had quite a hard life, and so they're not in the best condition. So major bodies of water probably didn't appear on the surface of the Earth until the surface temperature had dropped to about 25 to 100 degrees Celsius. Obviously, less than 100 degrees Celsius, liquid water is perfectly happy. So there may have been bodies of water on the surface of the Earth at temperatures above 100 degrees Celsius very early in the Earth's history, and the reason we think this is possible is because the Earth's very early atmosphere would have been extremely carbon dioxide rich. That would have meant it would have been a lot denser than the modern atmosphere, which means the atmosphere would have weighed more, so it would have pushed down on the surface of the Earth harder. So this added atmospheric pressure, because it's a thicker, denser atmosphere, would mean that the surface pressure would be higher than it is now, and this increased surface pressure would have been sufficient to have stopped water boiling at 100 degrees Celsius. In fact, the pressure would have been sufficient to have actually stopped water boiling all the way up to temperatures around 230 degrees Celsius. So, it is possible that we could have had bodies of water on the surface of the Earth very early on at temperatures which we wouldn't normally assume we would have formed these kind of seas and oceans. Now, modelling suggests it would have taken anywhere between about 150 to 500 million years after the Earth formed for the surface temperature to have dropped down to this 25 to 100 Celsius range. So it doesn't take too long for conditions to start to be correct for the formation of large bodies of water. Now, analysis of zircons, which date up to 4.4 billion years, most of these zircons come from the Jack Hills region of Australia, using oxygen isotope data, indicate that they grew from magma that may have formed from either a hydrothermally altered oceanic or continental crust or sediments. So what we're saying here is right, we've looked at these zircons, we've analysed them, and using the oxygen isotope values we get for those zircons, we can model the most likely set of scenarios to produce those oxygen isotope ratios. And the best options we can come up with is that the magma was produced from the melting of oceanic or continental crust that had been hydrothermally altered. Now, this hydrothermal alteration, the modelling suggests, would have been low temperature. Now, low temperature means that the hydrothermal fluids probably aren't magmatic or metamorphic in origin, so they're not going to be igneous or metamorphic fluids. Chances are what you're looking at is surface water that's been pulled down into the crust and is just being circulated around when it gets heated up a little bit. So what we probably got is surface water interacting with oceanic or continental crust, which once again would suggest that we had water present on the surface of the Earth during this period. If the magma in question formed from sediments, well, we also know that the vast majority of sediments are produced through erosional processes associated with water. And so that's also a reasonable piece of evidence to suggest there may have been liquid water moving around on the surface of the Earth during this time period. So although we can't tell exactly what the origin of the magma was, the probable candidates for what melted would suggest that there was liquid water. So we had a liquid hydrosphere on the surface of the Earth all the way back to 4.4 billion years. Now please bear in mind though, these are old zircons. Oxygen isotope values can be affected, and so the values may have changed over time. We can't be 100% certain, but this is decent evidence to suggest water all the way back to 4.4 billion years. Now this work is actually backed up by another piece of work, which is great. Now this second piece of work analysed zircons again, and they looked at the titanium concentrations in those zircons. And these zircons dated from between 4 and 4.35 billion years. So once again, we're back in the Jack Hills area of Australia. And this data indicates that the zircons crystallised from magmas of temperatures of less than 800 Celsius. So you're thinking, oh, cripes, that's pretty warm. The thing is most rocks are stable into a temperature range in excess of 800 Celsius. So to melt a rock at temperatures lower than 800 Celsius requires the addition of some kind of flux. And the most common flux is liquid water. So the fact that you have these magmas which seem to be, have a temperature of less than 800 Celsius would suggest the rocks that were melting to form those magmas were melting at lower temperatures, so temperatures less than 800. And so the best explanation as to how you can bring this about is by having the rock react with the water at temperatures of less than 800 Celsius, and this will then lead to the rock melting to produce the magma that gave us these zircons that we're measuring. So once again, it's another piece of evidence to suggest that yes, there could have been liquid water all the way back into this, anywhere between about 4.28 to 4.4 billion years ago. Once again though, these are old zircons. They have been, they have had a tough life, so, changes could have occurred, so the data we're getting may not be 100% accurate, but the fact we have these two different pieces of evidence from different studies does seem to suggest that there is a reasonable chance that there was liquid water all the way back to about 4.4 billion years ago. So we have to be careful, but the fact these two studies back each other up is a major positive. So zircon data must be treated carefully, of course, as we have small sample sizes, and the data is, of course, open to interpretation. So we can't be certain how extensive these early bodies of water were. But it's likely that additional volume was added to them during the late heavy bombardment. So there's probably these small bodies of water around, and then around the Hadean Archean transition, when we get this late heavy bombardment starting, chances are all that additional water added by comets helped to add more water to the Earth's budget, and so that will have increased the amount of surface water once the late heavy bombardment finished about 3.8 billion years ago. So another thing we have to deal with is the faint young sun paradox. So when the Earth was young, the sun would have been about 25 to 30% less luminous than it is now. So this would have meant that the Earth's surface temperature would have been about 25 Celsius lower than at present. So this would have brought many areas of the Earth's surface down to the freezing range. So this would have suggested in the Earth's very early history, the Earth would have been a giant ice cube essentially. So if, as some data suggest, the Earth's surface quickly cooled and water began to collect in topographic lows like we were just discussing, then it would suggest that during this very early phase the Earth's surface would have had lots of frozen water on it. However, the oxygen isotope data we were just discussing suggests that there was liquid water on the surface of the Earth during this time period. So obviously we have this slight problem. One model says we should have a whole load of frozen water. The other model clearly says no, there was liquid water circulating around. So which one of them is right? So the ability of any water to remain present in its liquid form on the surface of the Earth during this period can be explained by four variables. The first variable is greenhouse gases. So we're all familiar with the idea of greenhouse gases right now. These are gases that help to essentially trap heat on the Earth's surface. So the Earth's early atmosphere would have been extremely rich in carbon dioxide, which is a reasonably strong greenhouse gas. There would have been some methane around, which is a very strong greenhouse gas, and there would have been lots of water vapor around, which is a weak greenhouse gas. And so the combination of all these gases present in the atmosphere at that time in quite high abundances would have produced a much stronger greenhouse effect than we have now. So this would have helped the Earth to essentially retain heat energy from the sun. And so the Earth's surface would have been hotter due to the composition of the atmosphere. So that's the first thing that might have helped to have kept the Earth's surface warmer. The next thing that would have helped to keep the Earth's surface warm and thereby inhibit freezing would have been radiogenic heat. So obviously we've already discussed how the early Earth's mantle had a lot more radioactive elements in it. This means more radioactive decay, and that radioactive decay would have produced more heat. And this heat, in order to try and escape, a lot of it would have had to try and have conducted through the Earth's crust. And so this would have meant the Earth's crust would have been hotter than it is now. And so obviously this would mean the heat coming from the Earth's crust would be imparted onto anything on the Earth's crust, so it would have helped to have kept any bodies of water present a little bit warmer than they otherwise would have been. This also would have helped to have inhibited freezing. Another process at the time was tidal heating. So during this time frame, the moon was actually a lot closer to the Earth than it currently is. The moon has steadily drifted away. So this would have meant that there would have been a stronger gravitational attraction between the Earth and the moon. And what happens is as the moon orbits around the Earth, it literally tugs on the Earth as it goes. Now, we see this as the tides. So the tide goes out, that's the water being pulled towards the moon, and then essentially as the moon orbits round, essentially the gravitational pull stops and the water returns. So we see the tides ebbing and flowing. The same thing would have happened with the Earth. So whichever side of the Earth had the moon on it was being tugged and deformed by the moon. Not very, very strongly, but enough. And then, of course, as the moon continued its path around the Earth, well, it would have meant the area was being pulled would suddenly be released and it would contract and return to its original shape. So this would mean that essentially areas of the Earth were constantly being stretched and released, stretched, release, stretched, release. And so this is called tidal heating. Every time it's stretched and released, it imparts heat energy due to friction because the rocks start extending and moving past each other. And so because we had much greater tidal heating in the early Earth's history, it also would have added to the Earth's internal heat budget. And so that would have meant more heat would have had to have conducted through the Earth's crust. Once again, this is going to help to keep items on the Earth's crust warmer than they otherwise would have been. The final thing that would have helped to keep the surface of the Earth warmer than we would have expected is the albedo of, or should I say the bond albedo of the Earth's surface. So the Earth reflected less sunlight into space during this period. Well, if we can get more of the sunlight to be absorbed by the surface of the Earth, that means it's going to retain more of it. So what we really want is we want the Earth's surface to be covered by something quite dark. So a dark rock, or most importantly, substantial quantities of water, because the oceans are great at absorbing solar energy. And so the more water we have on the surface of the Earth, the more solar energy can be absorbed, and therefore the warmer the surface of the Earth will be. And so if the Earth's surface was either covered in very dark coloured rocks like basalt, or large quantities of liquid water, both of those would have helped the surface of the Earth to absorb more solar heat and thereby avoid freezing. So these four different processes working in tandem would probably have been sufficient to have inhibited freezing on the Earth's surface during this time period, thereby cancelling out the fact that the early sun was about 25 to 30% less luminous than at present. Okay, so now let's move on to the Archean. So the Archean accounts for about 33% of all geologic time, and it ranges between 4 billion years ago and 2.5 billion years ago. So Archean age rocks are not uncommon, and outcrops can be found on all continents. So great, they're everywhere, we can go around, we can find them relatively easily. However, we do have problems. They're challenging for three reasons. Number one, the main outcrops have often been metamorphosed and very complexly deformed, so the rocks are not in a great condition, they are not the original rocks. Most of these Archean rocks are deeply buried beneath younger rocks, so on the whole they're actually inaccessible to us. And obviously, as we've already discussed, these Archean rocks contain few fossils, and those fossils which are present are microscopic, making them not particularly good for doing any kind of, time stratigraphic correlation, or even trying to divide up the Archean. So, although the rocks are present, they are not easy to work with. So, now we need to have a think about shields, platforms, and cratons, also sometimes referred to as Cratons, depending on who's saying the word. So Precambrian rocks typically form the nucleus of the continents. So along the margins of these Archean core rocks, you have more material that's been accreted or deposited in the form of sediment. So we have these very old cores of the continents, and they consist mostly of Precambrian rocks, so Hadean, Archean, and Proterozoic. And what's happened over time is these cores have had material just stick themselves onto the side, so that's the process of accretion. So let's say a subduction zone opens up, the oceanic crust subducts underneath the piece of continental crust, and then every once in a while an island arc, like Japan for instance, would stick itself onto the side of the continent and get and attach itself onto it. So this would have made the continents bigger through accretion, adding material. Another thing that would have happened is these continents would have been above sea level. They would have been essentially exposed to erosional processes, and this would have produced sediment, and that sediment would have been transported by rivers and deposited along the margins of these early continents, again increasing the size of them. So these very early Precambrian continents would have started to have grown very, very quickly. Now, the areas where these Precambrian rocks are exposed are termed the shield. So in the shield, you can walk around, you can actually touch these Precambrian rocks. Now, where the Precambrian rocks are covered by later rocks, so younger rocks, so we can't get to them, they are termed platforms. So a platform is an area where the Precambrian rock is covered by Phanerozoic rocks, so you can't actually get to the Precambrian rock. It's there, but your only access to it would probably be through drilling. When you combine the areas covered by the shields and the platforms, that's what we refer to as the Craton or Craton, depending on your pronunciation. So both Archean and Proterozoic rocks form these Cratons, and they typically display a felsic to intermediate composition and are usually dominated by granite and gneiss. So these rocks are going to be dominated by lots of quartz, lots of potassium feldspar, some quite sodium-rich plagioclase feldspar, excuse me, and a few lower temperature minerals like muscovite, for instance. So Cratons display textures indicating multiple stages of mountain building, metamorphism, and volcanism. The process of mountain building is obviously a tectonic process, so the fact that we can see these indications of pieces of crust banging into each other suggests that during cratonic formation, plate tectonics must have been operating. However, most Cratons have actually experienced relatively little deformation since the Precambrian. So most of the action in the Cratonic environments took place in the Precambrian, and then as we moved into the Phanerozoic, things got a lot quieter. The reason for that is as we move into the Phanerozoic, we have new material being added to the edges of these Cratons, and this new material begins to act like a buffer. So essentially, every time something new hits the Craton, it doesn't actually deform the Precambrian rocks, it deforms the younger rocks. And so over time what happens is as more and more material builds up on the edge of this continent, the Craton in the middle gets more and more protected. And so since the Precambrian, more and more material is built up along the edges, and so that means Cratons haven't really undergone extensive deformation since the Precambrian. So this is helpful to us. Once again, we can say, right, the deformation we're looking at in most cases in these Precambrian environments is probably due to stuff that was actually happening in the Precambrian. And so that goes back to the fact that we have these indications of plate tectonics. So the exposed craton in North America is termed the Canadian Shield, and it covers most of northeastern Canada, a large part of Greenland, the Adirondack Mountains, so that's New York State, and also turns up in parts of Minnesota, Wisconsin, and Michigan. So the platform underlies much of North America. However, outside the shield, obviously the Precambrian rocks are only exposed in areas where they're uplifted. So there has to be some kind of tectonic deformation that takes these very, very deeply buried Precambrian rocks and pushes them to the surface. So we typically only see these Precambrian rocks in areas like the Rocky Mountains or the Appalachians. So if we look at this diagram here, what you can see is the red areas represent the regions of the Earth where we have exposed Precambrian rocks. So there's a shield environment, so you can go out, you can touch the rocks, you can walk on them. Whilst the green areas represent areas of Precambrian rocks which are covered by younger deposits. So in the case of North America, you'll see that the Canadian Shield is located here. We have portions of it here in in Greenland there, and we actually have portions of it over here in Scotland as well. So this area here is exposed, you can walk on it, but the green area, obviously that's the platform, the Precambrian rocks are buried. You'll notice though we do have a trend of Precambrian rocks occurring down here related to deformation for the Rocky Mountains, and we have a trend of Precambrian rocks exposed here. These are rocks that were exposed due to the Appalachian mountain building events. And so the only time we get these Precambrian rocks appearing at surface on the platform is when they're pushed to the surface due to very large scale tectonic processes, usually mountain building events. So Archean rocks account for only 22% of exposed Precambrian crust. The largest exposures are in North America and Africa. So the Archean rocks are dominated by a type of a type of environment called Greenstone Belts, and another type of environment called granite gneiss complexes. And it's these granite gneiss complexes that make up the vast majority of Archean rocks. And as the name suggests, these are areas which are dominated by granites and gneisses. Shock horror. So the granite gneiss complexes are mostly granitic gneisses, and granite, so this means there's going to be lots of quartz, lots of potassium feldspar, lots of sodium plagioclase feldspar, some muscovite, some biotite, and a few other things present. And these rocks probably represent felsic to intermediate intrusions emplaced into the crust during the Earth's relatively early history. So these are probably representing big balls of felsic or intermediate magma which are trying to migrate through towards the surface, but they get stuck in the crust where they crystallize out as the plutonic rock granite. And obviously over time those granites have been metamorphosed and turned into gneisses. Now, greenstone belts account for about 10% of exposed Archean rocks. However, they offer us considerably more information on Archean plate tectonics, and they're also important to us because they are a very important host of gold, silver, copper, lead, and zinc mineralization. So they not only have a usefulness from a geologic point of view of understanding what was happening, they also have a usefulness from a mining perspective as well. So it really helps us as geologists to understand these environments because not only will we understand the Earth better, but we will be able to find more stuff to mine and make some money. So this is the basic model that's used to explain the formation of the continental crust. Now, we know by the time we're into the Archean, about 4 billion years ago, we have indications that plate tectonics was working. Now, we can't be certain how consistent these plate tectonic processes were, but we know they were around. Excuse me. We also know that the Earth's interior would have been quite hot, so that would have meant quite a lot of magma generation. And so what would have happened is we would have had probably some subduction, and we would have had the pooling of magma at the bottom of the lithosphere, and both of these events would have produced quite large volumes of felsic and intermediate magmas. Now, I'm not going to go into those processes. We discussed them right back at the start of the course when we were talking about the genesis of igneous rocks. So essentially all this melting produces lots of felsic and intermediate magmas. They will obviously make their way through the crust. Sometimes they'll get stuck in the crust where they'll crystallize out as coarse plutonic igneous rocks, so granites and diorites, and sometimes they'll make it all the way to the surface where they'll form a volcano, in which case we'll get volcanic felsic and intermediate igneous rocks like rhyolite and andesite. And so what you'll have is you'll have lots of these volcanic islands or volcanic island chains moving around on the surface of the Earth, riding along on top of the pieces of oceanic crust. And of course, because plate tectonics is functioning, the oceanic crust will be subducting in some places, and this will mean that island arcs will naturally be pulled towards other island arcs, and they will collide with each other. Now, because these island arcs are going to be made from rocks which are comparatively light, so granites and gneisses, they don't want to subduct. So the oceanic crust, that can subduct, that's fine, that's quite dense. But in comparatively speaking, the more felsic material is far lower density, and as such it will not subduct easily. So all these island arcs are just going to start crashing into each other, and it's going to happen again and again and again and again. And so this represents the early stages of continental crust formation. These island arcs hitting each other one after another, forming these small continental land masses. Now, we've already gone and discussed how, as more material gets stuck onto the edge, that will obviously increase the size of your continent. And obviously we also have erosion taking place in the center of this continent where the rocks are exposed, and the sediments produced being deposited on the margins of these continents, also helping to increase their size. So, that was granite gneiss complexes. What about greenstone belts? Because greenstone belts are actually more helpful to us. So a greenstone belt consists of three main rock associations. So there's a lower portion, a middle portion, and an upper portion. So the lower portion of your greenstone belt consists mostly of metamorphosed volcanic rocks, typically mafic and ultramafic volcanic rocks, so basalts and komatiites. The upper portion of your greenstone belt will typically be of a more silica-rich nature, and they are normally modelled as representing sedimentary rocks that have been metamorphosed. The sequence, so these lower, middle and upper units, are then commonly intruded and cross-cut by granites and thrust faults, because these areas are often quite tectonically deformed for reasons which we'll discuss in a second. So greenstone belts tend to be synclines, so they tend to have a trough-like shape to them, and they'll typically measure between 40 and 250 kilometers wide and 120 to 800 kilometers long, so some of them can be quite substantial. And this elongate morphology explains why they're referred to as belts. So if we look at this diagram here from the textbook, we can see this shows us the superior craton here in this light green colour, and these darker greens represent the greenstone belts of Canada, well, should I say, of Canada and also the United States as well. Now if we look at these greenstone belts, you'll notice they have a elongation direction, orientated like so. And you'll notice that these greenstone belts are orientated approximately parallel to each other. Okay. Now you'll notice the greenstone belts of the superior craton over here versus the greenstone belts of the slave craton. This orientation is slightly different. So these superior craton greenstone belts are orientated approximately like so, whereas the the greenstone belts of the slave craton up here are slightly steeper, a bit more north-south like so. So in terms of the greenstone belt itself, we obviously have our lower, middle and upper units. So the lower and middle units we've discussed are mostly mafic and ultramafic igneous rocks that have been metamorphosed. So this layer here and this thick brownish layer in the middle there. So those two are going to be our lower and middle units. And then we have our more silica-rich upper units, which probably represent metamorphosed sedimentary rocks. And you can see they've been deformed to give us this nice syncline right here. Okay, so remember, synclines, youngest rocks in the middle, oldest rocks on the outside. We can then see that these synclines, these greenstone belts, have then been intruded by granites. And so this will often mean that the greenstone belts will often have granites coming up in the gaps between the synclines, and so you end up with these synclines being separated from each other. So you can see that quite nicely here. We have one greenstone belt here, separated by a granite nice complex in the middle, and then the next greenstone belt there. So the volcanic rocks of the lower and middle portions are mafic to ultramafic in composition before they were metamorphosed. Okay, they've now been metamorphosed to give us a low medium grade metamorphic rock, which we call a greenstone. And it's called a greenstone because the rock has a distinctive green colour, and that comes from the presence of 3 green minerals: chlorite, actinolite and epidote. Those 3 minerals combined will help to give the rock a nice green appearance. So these greenstones form from mafic and ultramafic rocks, as I mentioned before, with a basalt protoliths displaying this pillowed basalt texture. So we actually have some of the original volcanic textures still preserved. Even though the rock's been metamorphosed, we can still see the texture present. And so this is telling us that the rocks which have been metamorphosed were probably basalts that had been extruded onto the seafloor. And once again, as we've discussed, most pillowed basalts are formed due to divergent plate boundaries. So that's a good strong hint that plate tectonics may well have been operating during this time. So yeah, the pillow texture indicates the eruption of mafic lavas onto a seafloor, indicating that greenstone belts represent metamorphosed oceanic crust. So these are modern pillowed basalts. You can see you have this kind of lumpy shape. So this is one individual pillow, and you'll notice that the pillows actually grow out of each other. So this pillow here grew out of that pillow there, this pillow here grew out of this pillow, and this pillow here grew out of this pillow. And you can see the same texture in these greenstones here. So number one, note the nice green colour. That's due to our chlorite, actinolite and epidote. But you can also make out the pillow. So if you look carefully, there's a pillow right there. Okay, so that's a pillow. And you can see another edge of one right there. And you can see another one right here. If you look carefully, you can see them more and more easily. And so what we have here is we have seafloor, basaltic seafloor like this here, that's been metamorphosed to give us the greenstone. So this is telling us that this, once upon a time, was the same as this. Within our greenstone belts, we also have these rocks. So these are called komatiites. Once again, they've been metamorphosed, so they're not the original rock. But komatiites have this very, very distinct texture of these very, very long, spindly crystals, these very, very long, spindly phenocrysts. They were once olivine crystals, very long, very slender olivine crystals. And they give this appearance that looks a bit like grass. And so the presence of these komatiites and this what's called spinifex texture tells us, what we're looking at. So it tells us we see the spinifex, we know it's got to be a komatiite, and so we know in this case this is the result of an ultramafic lava being extruded onto the surface of the Earth, probably onto the seafloor. So do you know what? This is probably quite a good place to stop part 2. So we're going to pause here, get up, have a walk around, go and get a glass of water, take 5 minutes to sit down and relax, and then please come back for part 3.